So for this example, we have that an explosion is recorded by two microphones that are 2 miles apart. Microphone M1 receives the sound 3 seconds before microphone M2, where we're going to assume the sound travels at 1100 feet per second and want to determine the possible locations of the explosions relative to the locations of the microphones. The first thing we might want to do here is think about what this looks like graphically in terms of feet, just so we can get a sense of the rough outline of what we're looking at here, where we have to think a bit carefully about the design for this. Because M1 got the sound 3 seconds before M2, and the sound travels at 1100 feet per second, we have that the difference in the distance from the point of the explosion P to M1 and the distance from P to M2 is a constant value of 3,300 feet. So the set of all points P that can describe the possible locations for the explosion relative to those two microphones is actually hyperbolic, where in particular we're going to look at the right branch of the hyperbola somewhat arbitrarily. Based on the picture we have here, we're making this a horizontal hyperbola centered at the origin, but you don't really need to. It just makes our math a little nicer if we do. The point is here we have a picture a bit like that where we can think of our values M1 and M2 as the foci of this hyperbola, where as we are working from around the center with a horizontal arrangement, we have x squared over a squared plus minus y squared over b squared is equal to 1, and our goal here is going to be to use the information we have to find a and b, where in this case, since the difference between these two distances is 3,300 feet, we have that 2a is equal to 3,300, that total distance. So a is equal to 1,650 feet. And we can use that to get a squared, but I'm going to leave that alone for a second just for the sake of nicety. On the other hand, if we want to talk about the value b, we can't get that directly in terms of what we have because it's kind of a messy thing with asymptotes, and we don't know quite enough to be able to describe the asymptotes, at least not directly. Instead, what we can do is think about this in terms of c, where in particular, because we're talking about this in the center being the origin, and these microphones are 2 miles apart, the distance that either is to the center is 1 mile, or 5,280 feet. That is, our value for C is 1 mile, or 5,280 feet. So we have A and C. If we want to find B, well, it's not going to be very pretty. B squared is equal to C squared minus A squared, which in this case is 5,280 squared minus 1,650 squared. And if you can get this value on your own, good on you. You're a lot better at math than I am, but I'd probably recommend some sort of computation to finish this guy off, where you would get that the value for B squared, that is 25,155,900. So we've got B squared, and if we want A squared, well, we just square A. That's not the prettiest number either, but what we'll end up with is the equation for the hyperbola being x squared over, oh boy, 27 million. No, wait, is it 27 million? No, it's actually not. 2,722,500 minus y squared over, well, that horrible mess, 25 million, and we'll call that some change, where this all equals 1. always equals 1. We're looking for the standard form. Where in particular, if we want to describe that sort of position, we're going to focus on the right section, but that's, again, like I said, a bit arbitrary up to how we chose to arrange things. Anyway, this is all I got for 9.2. Next week, we're going to move into 9.3. We're going to talk about things that are probably a bit more familiar. We're going to look at parabolas. And the nice thing with parabolas is I can actually anchor those to the real world a little bit nicer in ways that hopefully will give them a different sort of immediacy than what you've seen probably up to this point in terms of equations of form y equals x squared and its relatives. But that's for next week. I'll see you then.